Hello everybody and welcome to CS302 Online, video 10. Today we're going to be talking about Quicksort, and we'll get through the entire Quicksort algorithm and then we'll spend a little bit of time comparing it to merge sort, and that should be it. I think we will have time afterwards, and if we do, then we might start talking about some tree stuff, but if not, either way, the cutoff will be for the exam today. Why did Obi-Wan says hi? What? I'm confused. Anyways, so Obi-Wan, I'm not sure. What do you mean? Like, because I say hello there, basically, or what? But yeah. Anyways, let's get going then. So this time, unlike last time, I went ahead and got a list of numbers for Quicksort that is not going to give us some edge case. And this is literally an example that I've done in the past. So I think this should be good. Okay? So, oh, you always say hello there. I do, but then sometimes I don't, I guess. So I don't know. It's truly RNG. So yeah. So last time I kind of showed you conceptually how Quicksort works, but now we're going to kind of jump in and do it how it actually would work in actual implementation, and we'll talk about the pseudo code and everything, okay? But let's make sure we understand the basics of this. The basics of this is that we have a list of numbers. It's in some sort of array, and what we're going to do is we are going to pick one of these numbers to be our pivot, okay? Now, picking the pivot is a complicated task because at the end of the day, the perfect number for the pivot would be the median. What is the median? Not necessarily the average, but the median. The median is typically the number right in the middle of the list, right? Which means that there's like X amount of numbers before it, and that X is going to be equal plus or minus 1 to the numbers on the right, okay? That would be perfect because if we could split this list in half every single time, then we would basically be cutting the job of Quicksort in the fastest possible way, log n time, okay? Essentially, and we would achieve n log n time, kind of like merge sort. However, picking that medium number is not easy because identifying a medium number would require us to scan the entire list to look for such number. And that would make the algorithm take n squared time. So no easy way to be able to look at the numbers and pick that. So the next best thing is to pick a number at random. Why? Because if I ask you, you know, if I have a number, if I'm thinking of a number between 1 and 10, okay? And right now, you know, I'm thinking of a number, let's say, and then you guess that number. Statistically speaking, every number in the list has the same amount of chance of being correct, right? But if I told you that you would get the most points if you were the closest, you would be better off guessing somewhere in the middle because you have a better chance of potentially hitting the number there. If you pick something like 10 as your guess, then unless you get lucky with 10, it's the furthest away you can get from like 1, right? And so this is an oversimplification of some math, but ultimately, by picking a number at random, you have the best odds of picking something that is relatively in the middle of a list, okay? Like there's better odds of that. And so that's really what is best to do for picking a pivot. It's just to pick a number at random. Now, whichever number you do pick for your pivot, so that the algorithm works the way I explain it, you want to move it to the end of the list, okay? So the easiest thing is just to pick that last number. So pick this 18 right here. However, if the algorithm by random, you decide that you're going to, you know, kind of like roll a rand roulette that's going to hit a number between 0 and 7. And wherever it lands, that's where you're going to pick as your pivot. What you do is move that number to the end by swapping it with what's currently in the end. So like, let's say that you pick 37 to be your pivot for some reason. Then you can swap 37 and 18 and just end at the end of the day with the pivot right here. There are other ways of doing the algorithm where your pivot could be like in the beginning, for example. It could be technically anywhere. You could come up with an algorithm to do it that way. It's just that the way that I'm going to show you, the way that's more, I'd say, popular, is to go with what I'm saying, which is to keep the pivot at the end. Okay? So, pivot. Next. What I said about what you do with the pivot and with the list is, what you need to do is, you need to split the current list into two lists. We need to partition this list into two lists. The partition on the left is going to contain all of the numbers that are less than the pivot, and the partition on the right is going to contain all of the numbers that are greater than the pivot. And this is because we are sorting in a non-descending, or more commonly known as ascending order, right? If you were to do the other way around, then just flip the logic. But essentially, that's all there's to it. You just split the current list of numbers into smaller than and greater than. You got duplicates. Stable isn't really, or Quicksort isn't really stable, so it doesn't really matter as much. But to make your life easy, put them on the left side. So left side here, and I guess the mirror this side left. And where do you put the pivot? That's kind of important, because here's the thing. The Quicksort I'm going to show you, which is the better way of doing it, I suppose, is to do it in place. So you don't need extra space to do it. And so you need to have somewhere to put the pivot. And it turns out that every time that you run an iteration of Quicksort, at the very least, you are going to sort one number into the correct spot. And this mirrors kind of like bubble sort, because if you think about bubble sort, every time the bubble sort runs, every time it runs, it puts one of the numbers in the right spot. It actually bubbles the biggest number to the end, and then the second biggest number, and so on, right? And it takes n squared time, because if every time it runs, it just sorts one number, and there's n of them, then it's going to be basically n times n, which is how you get the n squared. With Quicksort, in the worst case scenario, which is what we actually saw last time, which, as a reminder, was these numbers here, we were basically bubbling all the numbers to one side or the other, and it wasn't really splitting it evenly. So every time that you run it, we actually only sorted one number. So that was pretty bad, worst case scenario of Quicksort. And so that is why in the worst case scenario of Quicksort, the big O is actually n squared. So yes, Quicksort has an O of n squared versus merge sort, which has an O of n log n. However, Quicksort on the average is actually faster than merge sort. So it's a little bit of a not confusing thing, but of a sort of a misleading thing to think about, because the big O is slower in Quicksort, that it's not as good, because it is. It just happens to be that if you're scared of getting that worst case scenario, then you better stick with the merge sort. So I suppose by that token, you know, you take a little bit of a risk by using Quicksort. You're like, okay, yes, it's faster. Yes, there's a chance that it's going to be really bad, but it's such a rare case in practice that I'll take the risk, per se. Okay, so that's pretty much it. We're going to split it into two lists, and you're going to keep the pivot in the right spot of the list. So even though the two lists that we're splitting are not sorted in themselves, we are making the pivot go on the right spot. Okay? Consistency over optimal in better cases. Consistency over, but that's the thing. Quicksort is consistently better than merge sort. But there are special cases. So I would say consistency. If you care about consistency, then I would go with Quicksort, to be honest. But anyways, all right. So let us go ahead and there's on Canvas I have an animation that I would normally show, but copyrights and whatnot, I want to show it. So we're gonna not do an animation. But if you want to see an animation of the algorithm, you can check out Canvas for that. The Canvas page on Quicksort reference, where there's also the YouTube for the link for the other YouTube video. So what we're doing, because we're doing this in practice, so we can imagine that this is an array. I went ahead and numbered the indices of the array, and I have two integers that are pointing to different indices. I have low and high. Low is going to start by pointing to the first item in my array, and high is going to be pointing to the last item in my array. Okay? So what I'm going to do is I'm going to slowly work my way so that low moves this way and high moves this way. And when they basically touch each other, and by that I mean they're in the same spot, that's when I'll be basically done. Okay, well, I'll still need to move around the pivot, but that's just a one last step. Okay, so I will explain to you one iteration of it first, and then we'll come back and try to come up with the pseudocode of that. Okay, but first I just rather explain what is going to happen. So the end game is, again, we want to, because we're doing it in place, we want to shift the array around so that the pivot is in the middle. Not exactly the middle, but by middle I'm saying that everything less than is going to go on one side over here, and anything greater than is going to go on that side, okay? So it's a lot of talk to get going, but I just want to make sure that I don't lose you. And if I do, then let me know so I can find you again. All right, so I guess I'm going to actually copy this one more time since I'm going to be doing a lot of copying and pasting probably, so I'd rather keep a clean version of it down there. So maybe start on the next page like that. So remember, we do have some extra variable here, which we'll call the temp, which we're going to use for the swapping, right? But that's all we need. Auxiliary space for Quicksort is just one. So one slot, and then the array. Okay, so we start by looking at either low or high. Typically, you want to start with looking at the low, okay? So you look at low, and you compare that with the pivot. If low, and by low I mean what low is pointing to, which in this case is 21. So if low is less than the pivot, then that's a good sign and we don't want to touch it. So we can just increase low. However, that's not the case here. Low is higher than the pivot. So we actually need to move low to the other side of the array. Okay? And by the way, I should point out, we are doing horse method, okay? Because there's another method for partitioning, which is called Lemurs, which we'll go over later. Okay? But first horse, because that's a better method, frankly. It's not, it's actually faster method, okay? So 21 is bigger than 18. So low is actually bigger than our pivot. So we need to swap it with something. So we need to put it to the other side, okay? At this point, we hold off on low and we look at high, okay? So high currently has a 17 in it, okay? Well, high has a 6, which is pointing to index 6, which means it has a 17. 17 is smaller than the pivot. So if high has a number bigger than the pivot, we don't mess with it. We would, in that case, decrease high by 1. So that means we look at the next number, so we look at the 42. But it turns out that here, that high is smaller than the pivot. So now we have a situation where the low is bigger than the pivot over here, and the high is smaller than the pivot. When that scenario happens, we swap them, okay? So I'm gonna take 21, put it in my temp, take 17, swap it here, and then do that, okay? Once I do that, I can go ahead and run my checks again. Is low smaller than the pivot? Yes, it is. Good. In this case, I can finally move low ahead. So I increase it by 1. So now low is looking at that. At this point, I have two choices. I can either look at high or I can keep running with low. So I'll just keep running with low. Okay? So now I'm going to look at low again and see if it's smaller than or greater than the pivot. In this case, low is greater than the pivot. That means that I need to swap it with something. So leave it like that and go look at high. All right, I am looking at high here. Hello, high. High is looking at 21. Is 21 greater than the pivot or smaller? 21 is greater than the pivot. So that means I can't swap it with 46 because I will be swapping something greater than the pivot with something greater than the pivot. In that case, what do? I decrease high. Okay. Is that greater than the pivot or smaller than the pivot? It's still greater than the pivot, so I haven't found something that I can swap 46 with. So what do? I keep decreasing it. I'm basically going to keep doing it until I find something I can swap it with or I run out of things to look at. 91 is greater than the pivot again. Still can't swap it. All right, I arrived to 11. 11 is smaller than the pivot, so great. I have found something that I can swap 46 with. So I can perform now the swap. Okay, so I'll put in my temp, Put that there. And do that. Okay, now I can go back to working with low. All right. So low is something smaller than the pivot, so that's good. So I can increase it by 1 because I don't swap anything. And I guess I'll put it like this so I don't overlap it. But now I'm looking at 37. 37 is bigger than the pivot, so I need to find something to swap it with. So I look at high. 46 is bigger than the pivot, so it's a no-go. So now I'm looking at 37. 37 is still bigger than the pivot, so it's a no-go. And low and high are now pointing to the same thing. I never updated it, but now the low has a 2 in it and the high has a 2 in it. That's a sign that I'm done with the partitioning. All that remains now is to put the pivot in the right spot. So where does the pivot go? Okay, the safest thing to do is just to do an extra check and say, is low or high, which are both pointing to the same thing, is that number smaller than the pivot or greater than the pivot? If the number is smaller than the pivot, then go ahead and put the pivot at low plus 1, so at index 3. That way you don't mess it up. If the number is higher than the pivot, then you swap it with that number. In this case, 37 is higher than the pivot, so we are indeed going to go ahead and swap it. And remember that this is the spot, I suppose. I guess you don't have to, but to make your life easy, just make sure that you kind of know, okay? Which of the two it is. If it's, because just remember which one you swapped it with. If it was with this one or the plus 1. You can do that by updating the pivot is now equal to 2. Okay? You have now completed one iteration of the Quicksort algorithm. Let's go ahead and look at this list carefully. Notice something, which is not something new, but something that I've been trying to tell you for a while. Notice that all the numbers to the left of the pivot are smaller than the pivot, and all the numbers to the right of the pivot are greater than the pivot. And I can bet you $1 million that in the final sorted list, that's where 18 is going to go, in spot 3 of the list. Index 2, which is the third spot. So 17 and 11 are not sorted, but as you can see, when we flip them to sort them, it's still going to keep 18 in the right spot. And on the other side, that is not sorted at all. But I can guarantee you that when we do sort it, 18 is still going to be in the right spot. So with this iteration of Quicksort, we've technically only sorted one item, which is the 18 is in the right spot. However, if that was the case always, then the Quicksort will be n squared. But what happens here is that the other items are in the right partitions, right? And the partitions are much smaller now and easier to work with. So the list doesn't look, see, this is the thing about Quicksort. Merge sort and bubble sort and selection sort, even pretty much every single algorithm we talk to for sorting, as this algorithm gets closer to finishing, the list itself, like you look at the list and it looks closer to being sorted. Quicksort's not like that. Quicksort looks like the list is not sorting itself that well. I mean, yes, if you were to see the pivots, you start to see that the pivots are in the right spot. But like, if before I talked about Quicksort, first day of class, I came to you where I was talking about bubble sort, and I said, there's this sorting algorithm that like, you look at this list, and then you look at this list, and like, this is actually much closer to being finished than this one. And you'd be like, they both don't really look like they, if anything, it looks like more unsorted than sorted, because the 17 is like in the beginning now, and that should go later, and you'd be like, it doesn't look more sorted. That's just the way Quicksort works. It's like the list looks unsorted until we're almost finished, and then bam, it just looks sorted. Go on Wikipedia, and if I remember correctly, in Wikipedia for Quicksort, I think for all sorting algorithms, they have these little bar plots that are showing the sort. You can see again how the final product is going to be basically a line like that with a bunch of bars with a line like that. And so all the algorithms, the line, you can start to see it take shape. But with Quicksort, it's like building parts of the line and then other parts, and it looks confusing until it actually finishes and you're like, bam, sorted. So it's interesting to visualize those things. I believe Wikipedia I could probably show, so I might show that later since that's not not copyrighted, I suppose. So anyways, cool. So I don't see any questions or anything, so I'm going to go ahead and keep going with the algorithm. So the next step is to do the same thing again, recursion. So what I'm going to do now is I'm going to take each of the partitions and apply the same algorithm. The only, I suppose, care that I must take is that now low and high are not going to be 0 and 7, but they're going to depend on what the partitions left over are. So somewhere in this algorithm, or sorry, in this data structure, I have a size variable, and that size is probably equal to 8, because I have 8 items in this list. Do I have 8 items in this list? 2, 4, 6, 8. Yeah, I do. Okay? And so what I'm going to do to build the next 2 partitions, or what the recursive call is going to be, it's going to be something of this format. And again, this might be a moment when I can start doing some pseudo code, but the recursive call is going to require what the new low and high should be. And so to compute the new low and high is, you want to have 2 recursive calls. You want to have the left recursive call and the right recursive call. For the left recursive call, you're always going to start your low at 0, like no matter what, unless you finished, in which case it'd still be 0 for that one last call. Similarly for the high one, so we'll say this is going to be the low and then the high. For the high one on the right side, it's always going to be the size minus 1, right? Because that's the last valid index. Okay? Now, the quote-unquote hards, but I wouldn't really call them hard, you just have to know what to do here, is to compute the new low in this one or the new high in that one. What you need to do is you need to see where the pivot is, and then base your high or low on plus or minus 1 that. So for example, if you're looking at the left side, the new partition is the one in red, okay? So you basically want to pass pivot minus 1. So that's why I told you, like, make sure you remember where the pivot went, if it went plus 1 or minus 1. Because what you want to do, you want to pass the pivot minus 1, and that's going to be your high over here. On the other hand, for the low here, it's going to be the pivot plus 1. You don't want to pass the pivot itself to the next iteration of the algorithm, because the pivot has already been sorted. That's in the right spot of the list. So you don't want either of the 2 partitions to touch the pivot. That's like, even though it doesn't look sorted, that is at least sorted. Like I showed you and proved you that. So don't touch it, basically. It's like, do not touch, So you're going to do that. You're going to pass pivot, not low as you put there, but you're going to put pivot plus 1 and then pivot minus 1 for the other one, okay? So that will take care of updating your low and high for the next run. In terms of the size can still remain the same. That's not a problem. And do you need any other? I suppose you would want to pass maybe like a pointer to the array, So let's say this is an array and it's called R. And I guess in that case, or the object. And if it's an object, then that's okay. But if it's not an object, then I guess you would need probably the size. Might be a good idea to pass the size as well. I guess technically speaking, you don't necessarily need the size. Oh no, because if you pass the size, you're gonna run into issues with that for that call. So if you're gonna pass the size there, then you actually don't want to pass the size. You want to pass the high. That would be on this scenario. So you want to pass size minus 1 there. So I think trying to see which way I could show you that would be like easiest. Yeah, you don't. I guess we'll pass a parameter here. It's unnecessary to pass it, but we'll pass it anyways, just so we can keep track of the size in an easier way. Instead of passing the size itself, pass the high. So I guess pivot minus 1, and in this case, size minus 1. Oh, well, it's size, so no minusing, I suppose. because it's size is plus, not an index, right? So you don't really need to pass that parameter, but that way this parameter here works okay. If you just want to get rid of the size entirely, I suppose you can, but in that case, this parameter of size minus 1 would have to become what would be the old high minus 1, okay? So you'd have to keep track of the old high. So when you call this function, you have a low and a high there. You're gonna potentially have that somewhere, right? And so that's the one that you would want to pass there. And the reason why I say old is because, like, see, I've been updating it here. So you need to keep track of what it was originally before any of the updates. So you can copy that over to a new variable or something, okay? And then pass that in. And then if you do that, you don't need to use the size at all. You can just completely eliminate the size. So really, you can just make that your functions. Don't need to worry about the size at all. Simplify that, get rid of that, and just pass that in. Some sort of old high. And then, yeah, that should be good enough, okay? So, all right. Let me, before I do the next iteration, write down the pseudo code or conceptually what I'm doing for the cases here, okay? So first, let's talk about the low part that I said. So we're looking at the two things, right? We're looking at the contents of the low and the contents of the high. And by that, I'm not saying the value of low itself, but what that index contains, right? So if low is 2, I'm not comparing the number 2, I'm comparing the number 18, right? So while in code you'd write something like AR low, in the pseudo code for not having to write too much, I would call it low, okay? But you know that I'm talking about like the contents, okay? So if the low is greater than the pivot, in that case, you want to swap it. Okay? But what are you going to swap it with? Well, you're going to swap it with high. I'm running out of space here. Oh, I erased by accident. If and only if the high is less than or equal to the pivot. Okay? So only in the scenario where the high is less than or equal to the pivot, you swap. Okay? Otherwise, if the low is equal to the pivot or the low is less than the pivot, then all you're going to do it is just increase the lows counter. Okay? And this is referring to the counter, not to the index, okay? Or it's referring to the index, not to the contents. Swap low or the pivot? Oh, swap low, not pivot. So I guess I put swap low. Like that. The pivot never gets swapped until you're almost done. Like until low and high are equal, that's when you're gonna swap the pivot. Okay? I suppose I feel like I will lose you if I don't put the thing. So I might do like the index like that. Okay? That way you don't get confused. So I'll put that in. We'll call it A, not R. It's less writing. Okay? And same here. You're not swapping the index, you're swapping the contents of the index. But see how it can become a pain to write all these square brackets? Okay? All right. So if the contents of low is greater than the pivot, swap low with high only if high is less than or equal to the pivot. Otherwise, low plus plus. Oh, no. You don't want to put it like that. No, this is good. This is good. Okay? So, here's the situation though. I'm going to put some space so I can put it. Right? What happens if A is not less than the pivot? What do you do in that case? Okay? In that case, you need to find a value from high that is less than or equal to the pivot to swap. Okay? So how do you do that part? How do you find that part? So that's when we're looking at the high part. Okay? So with the high, when we start high by setting it to the end. And what we're going to do is we need to find something to swap it with. And if we can't find something to swap it with, then we give up. Okay? How do we give up? When low and high are equal to each other, the indices. So essentially what you need to do is you need to put this in a loop. That is going to basically loop while A high is not less than or equal to the pivot. Go high minus 1. Okay? So let me go ahead and write that loop here. Well, A high is greater than the pivot. I think that's what works better. Go ahead and say high. Okay, by the way, why am I using these colons and equals like that? It's a better way of explaining that this is assignment operator versus like equality in math. Okay, so that's why I'm using this symbol here. All right, because it's assignment like that. What we use equal for in C++ can be confused when you're writing an algorithm with like actual equality, and you don't typically see people writing equal in like pseudocode, so they use that to signify the difference. Okay. So while A high is greater than the pivot, go ahead and keep decreasing it, okay? And so that is the kind of loop that you need to run to find something, okay? So we need to add in here a scenario where what happens if it's not? What happens if A high is greater than is less than or equal to the pivot? In that case, actually that's going to be outside the loop. My bad here. There's going to be two possible scenarios that are going to happen after this exits the loop. Okay? One of the scenarios, well, we actually have to consider that. One of the scenarios is that we don't find something, right? So that would be if high is equal to low. All right? If high is equal to low, we have not found something to swap it with. Okay? If that is the case, we still want to break out of the loop at this point. Okay? Once we're out of the loop, there's two possible scenarios that we have to consider, okay? Again, the same scenario where high and low are equal, or the scenario where we found something to swap it with. So we can do that by doing that with a simple if statement. We can say if A high is less than the pivot, less than or equal to the pivot, then you can swap it. Okay? Alternatively, the other scenario that you might run into is, again, if high and low are equal. Okay? In that scenario, you're done. Okay? So you can move on to the last step. The last step has two cases. The case one is that, and doesn't matter which one you look at, so let's just look at low. So if low is less than the pivot, then you're really done, I suppose. Or sorry, no. you go ahead and you swap a low plus 1 and the pivot. So here you're actually swapping the pivot. Alternatively, the other scenario is, I suppose, less than or equal to might make it easier. The other scenario is with that a low, and I'll put it here as a comment, I suppose, because I just want to make sure that you understand that in this case, a low is greater than the pivot. You know, that's kind of what's happening in this scenario. In that scenario, you're just going to swap a low with the pivot. Okay? That's it. And that's pretty much the full algorithm. All that we really need to do is now we just gotta kind of organize it together into actual code, right? But these are basically all the steps that we have in the algorithm. We have checking low versus the pivot. And then if we do need to swap something, then we have to check high, which is this fine part here that we're looking at is basically the loop here. And then after this code, so that would be like here, would be this part here. Okay? I guess actually I didn't all the way here like that. Okay? So, yes. And then this part covers all the way there. Okay, so that's all we gotta do. We gotta just kind of, it's kind of hard to show everything, but really that's the full algorithm. When you see the orange, the pink is where you're gonna put the loop, and when you see this little marker here, is where you're gonna put this part of the code. And then the algorithm is complete for the most part. The only part that we need to kind of add in here is at the end of the two recursive calls, which are these ones. Okay? So you put those, I suppose, like at the bottom of everything. So like all the way down here. Okay? So does that make sense, or would you like me to like write closer to actual code? Okay. In that case, let us continue with the actual case that we have here. Trying to highlight it. Hold on. Okay. So now we are running another iteration of this. So we're gonna say we're gonna do the left side. Okay, so the left side would be basically Quicksort 0, 1, name of the array, and that's it. Okay, so that means that low is going to be set to 0 and high is going to be set to 1. So we got to pick a pivot. I suppose that's the first part of the algorithm. So I guess we could throw that in up here, pick the pivot, which is just set the pivot to be the last item. So set the pivot equal to high. And so the pivot in this case is going to be 11. Okay? So we start by looking at low. Is low less than or greater than the pivot? Low is greater than the pivot. Sorry, yeah, low is greater than the pivot. And so in that case, we don't increase low. We switch over to that other loop, the one with the fine part, so the pink code. In that one, we start looking at high. But here's the thing. Oh, sorry, I made a mistake. When you start this, in this special case, when you start the algorithm, you got 0 and 1, right? Because you picked the pivot to be 1, it actually turns out that high is going to contain 17, not 1. So 0. Yes, because You don't want the high to be pointing the same thing as the pivot. Otherwise, I feel like you might get caught in like an infinite loop or something. Like, I don't know, or you might break things. So yeah, so normally, like your low, you got your high, and your high that you originally passed in from the function. Because remember, if what we wrote up here for passing for high is basically on the left side on the left side of the pivot -1, right, for the left, right here. So that's passing the 11. But you don't want high to be pointing to the pivot. You want it to point to the one before the pivot. So in this case, low and high are actually pointing to the same thing. So when you start the algorithm, you look at low, you see that low is greater than the pivot. You look at high, you see that high is greater than the pivot. So you decrease, you're going to try to go and decrease it, but you find out that low and high are equal to each other, at which point that means you're technically done. So you swap. So you go to the part where you got to swap the pivot. You see that because this is greater than the pivot, you don't need to +1 it. Otherwise, you would swap 11 with itself. You just swap 17 with 11. So big. You know, you run through the whole code, but really there's nothing much happening. You just basically swap 11 and 17. Okay, and that pretty much concludes that part of the of this side of the algorithm. Okay. So there's going to be technically one more recursive call that's going to happen here. Or actually, if you write the code nicely, you don't have the recursive call. But even if you don't, you could return it. Because here's the thing: you can add an if statement at the beginning of your quicksort call, saying if low and high, or so if 0 and 1, in this case, if they were equal to each other, then just go ahead and return. Don't do anything. Okay, you could do that and you could be done that way. Alternatively, before you do the recursive call, check if low and high are equal to each other. And if they are, don't do a recursive call, because that means that you're essentially done, because your remaining list is one item. And one item means that it's already sorted. It's impossible for a one item list to not be sorted, because it's just one item. It's sorted. Okay? So that's a lot of talking for basically nothing there, because it's just a small scenario with just two numbers. But we'll see something more interesting on the other side. So let me just copy the high and low, because they're nicer looking this way. I messed up the arrows already. So okay, so that basically concludes that one. So now we're going to do the second recursive call, which is the one that would have, when we call it here, we would call pivot +1, so that would be 3. So we're doing 3, comma, and then the old high, potentially -1. In this case, because it's the first time that we call this, the old high would have been the size. So size would have been 8, -1 would have been 7. So you're passing essentially to this 37a. Okay, so that's what we're basically getting. So let's just copy and paste that down here. Okay, so 3 and 7. Okay, so 3 means that this is pointing to the 46. 7 means that originally this is pointing to the 7, but again, we're not going to make that same mistake twice. So we're going to decrease it by 1 again, so it's really going to point to the 6 as I had it there, but because 7 is going to be the pivot, okay? So you decrease high by 1 so you can identify the new pivot, which is going to be 7. Okay? Does the left side get sorted first? It depends on your recursion. So at the bottom of your code, you have these two recursive calls, left and right. If the left recursion call happens before the right one, then yes, the left side of the list is going to get sorted first. In fact, you will see the list being sorted from left to right in chunks. The chunks won't be like continuous, but it's going to be like this. So if this list was being sorted with left recursion, the first part that you would see sorted would be like, I mean, this is kind of not, this is misleading because that assumes that all the pieces are going to be split nicely. So here, let me do a more realistic example. So the way you're going to see this is first you're going to have a list. It's going to get split about in half. Maybe you get split about in this half, and then in this half, and then this part gets split like this maybe, and then this part gets split like this, and then this one gets split like this, okay? So the way this is going to get sorted is, first, this part's going to get sorted, and then it's going to come back from that recursion, and then it's going to run the other one. So I think then this side would get sorted, and then I think this side would get sorted, and then this part, and then you would start with this side, and then you probably get like this side sorted. So it's going to be sorted in kind of a weird sort of checkered way, I think, okay? But it's going to work its way from left to right, essentially. If you have the left recursion first. If you flip the left and right recursion, it's still going to work, but then it's going to start sorting from the end to the beginning, okay? So it'll be kind of in chunks like that. So anyways, now we're looking at this. And so we start with low and high, and we have low equal to 3 and high equal to 6. And so we look at low, and we see that low is greater than the pivot, so we need to swap it. So then we start looking at high. Run that loop. High is going to be 6, which is smaller than the pivot, so we have found something that we can actually swap with 46. So that's perfect. So 46 gets 21, and 21 gets 46. Okay? Great. Now we can go back to our low loop and basically keep increasing that until we find something else that we need to swap. So just 1, and we find it. So now we got to look at high, and we got to run that loop again. Find something that we can swap it with. Well, that we can't swap with, that we can't swap with, and now low and high are pointing to the same thing, which means that we basically you have to just swap that with the pivot to finish this iteration. So in this case, actually, yes, swap it with the pivot, yes. So 91 and 37 swap. 37 and 91. And it happens that in this scenario, the list is now sorted. So we went from like one step of not sorted to like, bam, it just sorted itself. However, technically the algorithm is not done yet. Now we're going to have two recursive calls here. First of all, remember that this is our pivot. And so technically speaking, we are going to pass the blue sublist as one call and the other blue sublist as another recursive call. So you'd call Quicksort, and your low would be basically 3, your high would be 3 as well. However, again, if you put an if statement checking if low and high are equal, don't do that recursive call. But even if you do it in the top of the recursion, you could check if low and high are equal, at which point that would be your base case. So I would put it in both cases just to be extra safe. But yeah, so that recursion call will hopefully not happen. You will hopefully catch it, and because it's pointless. It's just a waste of time. The other recursive call is going to be Quicksort 5 and all the way to 7. Okay, so that's actually going to happen still. The algorithm doesn't know that it's done, only we know. And so you're going to get basically 42, 46, and 91 that are going to get called with 5, 6, and 7. Your low is going to be 42, your high is going to be 46, and your pivot is going to be this. Okay? And so you're going to start the algorithm, and you're going to see that 42 is less than the pivot, so you'll increase it by 1. And then it's going to be high, it's going to be 46. And then 46 is still less than the pivot. But at this point, because low and high are equal, you know that you're done. Okay? And now, because low and high are pointing to something less than the pivot, technically you swap low plus 1 with the pivot. If you look at the algorithm above, that's what we do. So what does that mean? The pivot swaps with itself. So 91 and 91 get swapped. So nothing gets changed. But that does technically happen. Okay? And so now, this is where the pivot is at. And that we are passing two lists again. We're passing this list. And technically speaking, there's a list here that's empty, but technically speaking, it will be passed. So the thing here is that that list is empty. And how do you know that it's empty? Because when you compare it with the previous size, you see that it's greater than. So that would be one check that you would do and be like, oh, well, this is it doesn't have to be out of bounds necessarily. It just happened that in this scenario it is out of bounds because it's on this side. But it's possible to, like, technically speaking, I guess I didn't point that out, but when we did 17 and the 11, that list was empty, right? Like when we were sorting 17 and 11 at the top here, you know, we called Quicksort on the 11, but technically speaking, we could have called it on the blank over here, right? But we don't do that because the old high is basically bigger than the smaller than the index of the new low, which would make no sense because again it's not inside of the array. Okay, so just an extra check to do so you don't mess things up. So anyways, this gets called only on the left side, which is going to get called with 5,6. So you do get that extra call. So when you do that call, basically 42 is both low and high are pointing there, and 46 is your pivot. Nothing happens. Technically, the pivot swapped with itself yet again. And again, hopefully in this case, you don't call Quicksort when low and high are pointing to the same thing. And here you don't call it because there's nothing on that side of the list, okay? So even though we finish here, the algorithm doesn't know that. It still did pretty much 1, 2 more recursive calls, okay? Potentially 4 if you don't check for low and high being equal. But no more than 4, otherwise you're like in an infinite recursion because you messed up your base case. So that's pretty much it. That's the algorithm. It's a lot of talking for something that is relatively simple, but I wanted to make sure that you guys followed along. Does anybody have any questions on horse method for Quicksort? I can do like a really fast example with other numbers if you'd like, if that helps. Otherwise, I will go on to Lemurs Method. Again, the only part is keeping track of low and high. That's the only part that's tricky. And you only do the swaps when low is greater than pivot and high is smaller than pivot. If neither of those cases happen, then high is the one that gets decreased. The only time that low gets moved is if that spot is less than the pivot and it's okay. Okay? Otherwise, don't mess with low. And high, that is more flexible to move, but it shouldn't move if what you're looking at is greater than the pivot. Okay? Yeah, as in, you want another example? As in, yeah, as it makes sense. I think there's like a 1-minute delay on the stream chat. So I'm assuming that that's answering to the question about another example. But okay, it's kind of bad, big delay. So I think I gotta figure out to not get a weird case, some numbers. How about I could do these numbers actually from the example of the yeah I could do these numbers. Is there a way that I can freeze this thing to see the numbers? No, that's unfortunate. Well, here I'll do these numbers. This is it from that video for the Lemurs sorting. So I'll do that list of numbers because he doesn't with Lemurs, and so we're gonna do them with horse method. So you get to see the difference. Okay, so I don't know. Like I hope this is a good number mixture, but okay. So we start out with low being, so initially the first time you run it, you set the low to 0 always. The first like ever iteration of this, like the first call, function call, because you gotta have an initial recursive call, right? So your initial recursive call for Quicksort is going to be 0, size -1 and the array. Okay, so that basically sets the low there. Technically the high is this, but again, when we get to the function, when we get to the actual function call, you're going to decrease that by 1 so you have a spot for the pivot, right? So that means that the pivot is really going to be here. Sorry, the high is going to be there and the pivot is going to be here. Okay, so let me number these indices. And here we go. Okay, so we got low and high. Low is equal to 0, high is equal to 6, and pivot is containing the number 4. So we start out by looking at low. Low is greater than the pivot. So we got to find something to swap it with, right? And just to be clear, there's two loops going on here, right? One of the loops is for low to increase, and one of the loops is for high to decrease. That's why this can become n squared. If there were no two loops, it wouldn't be n squared, I suppose. But I don't know if that's necessarily true because of the recursion as well. It's more about the recursion too. But anyways, there's two loops, okay? Low is increasing and high is decreasing. Like in your implementation of this function, there should be two nested loops, okay? So low is increasing. In this case, because we started at 0. Well, actually, no. In this case, it's not increasing because 7 is greater than the pivot. So we stop there. We switch over to high to find something to swap it with. In this case, we see that high is pointing to 5. 5 is greater than the pivot, so that's not a good swap because it wouldn't help us. So high gets decreased by 1 until we find something smaller than the pivot, which we just did. So now we have found something smaller than the pivot, so we can go ahead and swap it. So we take the 7, and we take the 3, and we swap them. And now we go back to the outer loop, which is the one with low. In this case, low is going to be increased because it's less than the pivot, less than the pivot, less than the pivot, until we get to the 8. The 8 is greater than the pivot, so we enter the inner loop with high. High is greater than the pivot, but we got to find something smaller to swap it with. So it goes down by 1, goes down by 1. It's still bigger. So at this point, I'm going to put the arrow here, but it's technically pointing there. In fact, here, I'll just put it really close there. In this case, because low and high are equal to each other, whether it was because we got low up to high or high down to low, doesn't matter. If low and high are both the same index, that is your I am finished sign, okay? Get out of the two for loops at that point. Okay, I think that's the pin code that I wrote, where we gotta figure out what to swap the pivot with. The two candidates are this spot or this spot, always those two spots. The decision is going to be based on what low and high are pointing to. If what they're pointing to is bigger than the pivot, then you swap it with that. If what they're pointing to was smaller than the pivot, so like if 8 was actually a 3, then you would swap with the next index. So you would swap the 6 and the 4. But because 8 is bigger than 4, which is the pivot, then we will swap it with that. So you're swapping 8 and 4. And it makes sense, like from a practical point of view, because then you can see that 4 is in the right spot of the list, right? So, like it should, that won't help you when you're coding, but in the test it might, so you can remember how to do it. If we swapped 4 here and we left the 8 there, then that would be totally messed up, right? It would not, it would be in the wrong spot, the 4. Okay, cool. The next two calls that we're going to have are going to be, so we got to remember though that this is the pivot. So essentially we are going to pass, and then high and low are currently pointing to 3, and pivot is going to 3. They might not be the same. Again, it could be 4 if it be the scenario. So the two recursive calls are going to be Quicksort 0 to 2, and then on the other side, and how am I getting these numbers? I mean, maybe I should explain that again just to make sure you guys get it. It's pivot minus 1. And then on the other side, it's pivot plus 1. And then the old high, I suppose. And the old high, if it was pointing to 7, then you would leave it like that. If for some reason you were pointing it to 8, as in this it was a size, then you would do all high minus 1, right? You gotta make sure which one you do. Again, depends on the implementation. Okay? So that will take care of essentially passing 0 to 2, and here 4 to 7. Okay? What if the number next to 4, 6 in this case, was also smaller than the pivot? Would you still swap it with that? So that's impossible to happen, because what you're saying is we have a scenario where we have a number here, other numbers, and we have like the 8. So what you're saying is a scenario where we would have something like 4 and 5, right? That's impossible to happen because remember, for low and high to point to each other, high must have passed through this number, the number smaller than the pivot, which is after, right? And if it would have passed at that point, then it would have swapped it, right? If the number here was bigger than the pivot, it would have swapped it. And if it wasn't, then high wouldn't have moved. Low would have been the one that would have moved forward. So you never run into that scenario, basically. So don't have to worry about that. It's a good question though, but it should never happen if you code it right, I suppose. So, anyways, we got 0, 2, and 4, 7. So 0, 2 is going to be this one. Let me highlight them, I suppose. That's 0, 2. That's one of the recursions that we're going to do, and then this is the other one. Okay. So let us go ahead and let's do the right side this time. Let's say that the recursive calls were flipped, just to show you that both ways will work. So in this case, just to save time, I'm gonna copy down the numbers like that, 6, 7, 5, 8, and just the indices 4, 5, 6, 7. I hope that you've seen that this is in place. Like we don't need this extra array or something. Okay. So this is actually almost sorted, but it's still not really gonna. It's still not gonna be good for us, but we'll see. Okay. So this becomes low and this becomes high, which is, so the current value we got from here was a 7, right? But we increase that by 1 because we gotta give a spot for the pivot. So you can do that. I guess if you passed old high minus 1 in here, so if you pass the 6 here, then your pivot would be old high plus 1. Again, there's many ways of doing that. Just be consistent so you don't confuse yourself. So in my case, I'm going to be consistent and say that I'm always decreasing by 1 by my past value to get the real high and then to get the pivot, okay? So in this case, 6 is smaller than the pivot and high is also smaller than the pivot, okay? However, because low is smaller than the pivot, before I even look at the high, I'm going to increase this. Now I found something that is bigger than the pivot. So that's when I would actually look at high and see that it's smaller than the pivot, at which sign it would be oh wait, no, sorry. Low is still smaller than the pivot, so nothing would happen there. It would keep increasing at this point. So that would go like that. At which point, low and high are still smaller than the pivot, which means that the pivot swaps with itself, right? Because a low plus 1. So as you can see, that's why I was saying earlier, actually, that even though the list is almost sorted, it, you know, technically speaking, only the 5 is out of place. If we could just like slide the 5 here, this is not good for us because this is going to have another recursive call here, and then one with an empty spot here. So the next recursive call is going to be 4, 6, 8. Okay? So that one is going to have low be that, high be that, and then the pivot be that. At which point, no, we missed, oh, we forgot to start the pivot. No. 6, 5, 7, pivot. Okay, yeah, okay, cool. So we got this. So let me copy the indices down. 4, 5, and 6, okay? So in this scenario here, low is greater than the pivot, so we immediately go to high. High is greater than the pivot, so we decrease it by 1. So now high and low are pointing to the same spot. So now we got to swap that with the pivot. Because it's bigger than the pivot, we don't need to plus 1 it. We just need to swap them. So this gets swapped with this. Okay? And so now, this is the pivot, right? So the recursive call is going to be these numbers here. So as you can see, this is like a bad scenario for this because it's like, it's kind of going its worst possible way here, but oh well. So next recursive call, 6 is the pivot and 7 is both low and high, at which case nothing happens, but then the swapping happens with the pivot, so you get 6 and 7, okay? So after all of that, what we have left over, I'm going to zoom out so I can copy this. We have 3, 2, 1 on this side, which we haven't even looked at yet. Then we have the 4 that we first sorted, and then we have the 5, 6, 7, and then the old pivot 8 here, okay? So I think I got everything right. So now we look at this side and essentially pick the one at the pivot, 3, 2. They're both bigger. So essentially low and high go there. So you swap the 3 and the 1. So you get 1, 2, 3. That's nice because we're done now. But I mean, technically you get another recursive call there. That's the pivot. Nothing happens. Pivot swap with itself. And then you're done. Okay? So that's another example. I'm going a little bit fast because I want to show you Lemurs method. But yeah. Okay. So now I'm going to show you very fast Lemurs method. Lemurs method is not as good, but it's good to know. So there's a video, and that video is like 4 minutes long, and I think it does a really good job of explaining Lemurs method. So I would recommend that you watch that video, but I'll try and kind of go over what he does. I was gonna pick the same numbers, but I won't because he does those numbers, so that would be useless to you. So let's pick our original numbers that we had up here. Yeah, we'll use these for Lemurs method. And then you can see how these numbers were done with Lemurs method, if you watch that video. Okay, so if I remember correctly, this whole it's kind of like bubble sort, okay? So you still pick the pivot to be the last item, but now we are gonna, and he calls them I and J, low and high. He calls them I and J, but we are going to we're gonna keep the high and low naming convention to them. Actually, no, because they're not really high and low anymore. So I guess we'll use the I and J that he uses. Okay? Let me make this a little smaller. And then zoom in. Okay. So if I, let me make sure, he starts them out at the same one, I think, right? I want to make sure that I'm getting the right start as he does it. Yeah, okay. So he starts out by pointing J to the first element, so 0, and I is 1 minus the first element, okay? And so what he does is he starts out by increasing J until he finds an element that is smaller than the pivot, I think, okay? So he starts out by 21 and he increases this until he finds an element that is smaller than the pivot. So in this case it would be 11, okay? And so once he finds something that is indeed smaller than the pivot, what he does is he swaps it with whatever I plus 1 is pointed to. So in this case, he would swap it with, he would swap it with whatever I plus 1 is pointed to. So in this case, he'd swap it with 21. And then increase I to point there. So I has now 0. Okay? Once he does that, think about what is happening here. The fact that J went all the way until spot 3 means that anything before it, but after I, has to be greater than the pivot. And that's going to be useful to us because that means that we know that index 1 is greater than the pivot. And that is relevant, okay? So then we go ahead and we keep increasing this until we find something, again, smaller than the pivot. We keep increasing J. Finally, we find that 17 is smaller than the pivot. So what we do is, again, we swap that with something with I plus 1, which is going to be the next number that is bigger than the pivot. Okay? And this increases by 1. So I guess really you can implement this both without it pointing to -1 or pointing to 0, because either way you're swapping the thing next to it. It's always kind of lagging one behind, I guess. So anyways, once you've done that, you've actually already partitioned the list. As you can see, the partition is kind of happening at I plus 1. You can see that all the numbers on the right are bigger than the pivot and the numbers on the left are smaller than the pivot. All that remains is to put the pivot in the right spot. Where do you put the pivot? You put it at I plus 1. I think this is the part that he messed up in the video, because what you do is you just swap them. Just swap the pivot in that spot. In the video, he says to shift everything. Shifting stuff is slow. You don't want to do that. You can just swap it like that and be done. And then he puts it in the comment that that's what he meant to do. Okay? So now you're done with this iteration of Quicksort. Now you might be like, wow, this is faster. It's not. It's not faster. It's like bubble sort. It is not faster. Okay? The example he shows, even in the video, with these numbers, you can see how there's a lot of bubble effect going on there, which should give you a sign that it's slow. I don't know if we'll see that in this case, but I've never done this example with Lemurs Method. So anyways, you do the same partitioning system, I guess you still need some to keep track of like the left and right side, just so you make sure that the next time you run this with like that partition, and then you run this with this partition. We'll skip this one because it's already like done, so we'll go to that one for the sake of time. But let's go ahead and run Lemurs Method on this side. Okay? So, yet again, when you do the splitting, make sure you do it on the pivot, okay? Like, make sure you're doing it on the actual pivot. And this is the pivot. So, no 18 in here. Okay? So, we have indices 3, 4, and 5. Okay? So, again, start out by having your j equal to that first element and your I equal to 1 minus that. So 2. This method seems more easy. You know, when you see the video, the way he explains it, it makes it more easy. But I prefer the other method. I find the other method easier to implement and to practice. However, the other method, the one that I showed you first, is way faster in terms of actual runtime. So while this method might seem easier, it's slower. And if what you want is easy, you could just do bubble sort, right? Which this kind of is a little bit like bubble sort. So yeah, but anyways, let's go ahead and hurry up so we have enough time. So here we have 37 as the pivot again. So we pick the last number as the pivot, or whatever you pick as the pivot, just put it in the last number. And then again, you keep sliding j until you find a number that is smaller than the pivot, which we have immediately found here, okay? That's good that we saw this case. So technically speaking, you swap 21 with itself, right? Because you would swap this, the I plus 1 with itself. So in this case, I would become 3 now after you've swapped 21 with itself, okay? Once you do that, then I'm trying to think. I think at this point you got to increase. Let me think before I say something wrong. I think after you do the swap, you increase I, and then you keep, yeah, so I guess increase j by 1 at that point, okay? You have to increase j, because otherwise you would end up swapping 91 and 21, which you don't want. So yeah, so increase j at that point, okay? So yeah, all right, so moving on. So now j is greater than the pivot, so that's good. So you would go up to that. Wouldn't I equal to 2? I was equal to 2. It was equal to 2, but it got increased to 3. So like we started out with I equal to 2 in the beginning. Let me backtrack a little bit so you can see that again. So you initialize this by having I equal to 2, which is one number before, and then j equal to 3. Okay? That's the start. But then immediately you look that j is smaller than the pivot. So you got to swap that number with I plus 1, which is 3. So you're swapping 21 with itself. When you finish that swap, j goes up by 1, and I goes up by 1. Okay? So that is why I changed it to 3 after that. Okay? Because there's one swap that happened. It's just 21 swap with itself. Okay. So now we're looking at j, and j is greater than the pivot, so you don't swap it. You increase it. And you keep increasing until you find something smaller than the pivot, which in this case you don't. You finally end up pointing to the pivot. Because that happens when you get to the pivot, what you do is you swap I plus 1 with the pivot. So that means you're going to swap 91 with 37. So I guess this was a bad case for the algorithm, because we really didn't sort much except for one number, I think. Although, hey, actually, no. Technically, the list is sorted. But, yeah. Okay? But, yeah, technically speaking, you do more calls. You would call this with Quicksort 4,7 now. Okay? Let's run one more. Even though it's sorted, let's run it to that one last iteration. Just so you can see that nothing gets changed. Okay? So, yeah, because this is going to be weird. So now that we call this again, this is the pivot. And then we start out with I being equal to 3. And J being equal to 4. This goes all the way to the end. This is the part I'm not sure about because technically speaking now, we would want to swap the 37 with the pivot. But I believe you got to find a number that's bigger. Because otherwise if you swap it now, it's going to break the thing. Oh no, I see. Technically speaking, I'm going ahead of myself here. This is actually going to show an example of why this is inefficient. So we're running a little bit over on time, but I want to show you this. This is a perfect example. The list is sorted, right? But look at what happens here. J is equal to 4 and it's less than the pivot. So technically speaking, J is going to swap with itself and then I is going to increase to 4. Okay? We go up by 1 here. Yet again, 42 is less than the pivot. So it would swap it with I plus 1. So I plus 1, I has 4. 4 plus 1 is 5. It swaps with itself again. So this is inefficient again. And now I becomes 5. Then J gets increased to 6. Again, 46 is smaller than the pivot. So 46 swaps with I plus 1. So 46 swaps with itself. And then this gets increased to 6. You see how this is like bad? Not bad, but inefficient. Finally, J is going to get to 7, which is going to be the pivot. At which point now our code still works, which means swap I plus 1 with the pivot, which is 91 with itself again. So you do that swap, and now you technically would call this again with this partition, which the same thing is going to happen again. It's going to keep swapping with itself until it gets to the end and so on. So you can see that little bubble sort maneuver. But even so, the example he goes over, I recommend you watch it because those numbers bubble in a more obvious way. Okay? But yeah, that's basically Lemurs method. I don't go over as much in detail because again, it's the quote-unquote inferior method because it's slower. So, you know, why teach something? The whole point of teaching Quicksort is to learn a fast sorting algorithm. So I'll show you the fastest way. So that is why. However, I will let you implement either one for the assignment, I think. For the test, I may ask you both. So, FYI. So, that's pretty much the lecture. We have finished sorting, but I still want to talk about merge sort versus quicksort. So I will do that next class in the beginning for a few minutes, maybe. I might as well write this down now. I've been saying it quite a while, but the worst case of quicksort is indeed n squared. And then the omega and theta of quicksort are both n log n. And this says a lot about it, the fact that the theta is n log n, because that means that it's really rare for you to go to the n squared scenario, okay? That's like descending order or something that really screws up quicksort. But other than that, like quicksort is faster than merge sort. However, Tim sort is faster than either of them because it's a combination of two sorting algorithms. But as solos, you know, if we're talking like 1v1s, then quicksort wins as the fastest one. Yeah, for random data. All right, any questions? Quicksort is one of the hardest algorithms that we talk about, at least for the sorting. Oh, yeah. What's the difference between a dynamic array and a vector? Basically, vectors are implemented with dynamic arrays, but vectors are an object that have extra functions associated with them. So like, vectors have a function called pushback that inserts into a dynamic array. And so if the dynamic array was full, it can resize it for you. So if you created a templated class that contained dynamic arrays and had a bunch of functions, congratulations, you've implemented a vector. Of course, why do that when vectors exist? So hopefully that gives you a good cover all. Would limitative methods have the same time complexity? That's a good question. I think yes, technically speaking, it is n squared, n log n for the three of them. But in practice, it is slower by a certain factor that I don't remember. What happens when you get repetitive numbers if your low is 6 and your high is 6? Okay. I got to, which I'm assuming you're going with Hort's method. With Lemurs Method, I have to like see, but if you get 6, 6, 6, 6, 6, big memes, you got your low and you got your high and you got your pivot. So we said that you only swap if the pivot is greater than. If it's less than or equal to, you don't swap. So I guess in this scenario, low just becomes this, at which point you swap the pivot with itself. So I suppose a list with everything equal in it would be a n squared scenario of Quicksort. So that's kind of cool. So yes, that would be n squared, because every time it's going to go one by one. It's always going to. Yeah, that's cool. I like that. I hadn't thought about that. So yes, a list with everything the same is the Achilles heel of Quicksort. But also, yeah. As for Lemurs Method, brain hurts for that. How about I leave you guys that one to your own exercise? Otherwise, we can try it out next time, because I have to think about it. As you see, I'm not as familiar with Lemurs Method because, like, it's inferior. I'm going to get people attacking me for that. But it really is slower. It legitimately is slower. So, yeah. All right. Anything else? So the plan is Monday. So this is it, though. I mean, well, lie. The last discussion we have of Quicksort versus merge sort on Monday, that beginning of the class, that will be the cutoff for the test. Because I would like to have the discussion before, because it's technically sorting. But then after those 10 minutes, that will be end of the first test. And then the rest of that, which we talk about trees, will be for the second test. And then you will have your test on Wednesday, which there will be no class. All right? And we could also maybe save like a little bit of time at the end of class to do a quick review on Monday. How do you deal with the case when the right partition is empty in Hort's method? In Hort's method, if any of the partitions are empty, left or right, you don't do a function call. You basically don't do a recursive call. You will see that it's empty because you can compare your old values of low and high with the new values. And if they're trying to overlap, that's a sign you don't want to do that because you're breaking it. I'm sure you'll run into all these very weird special cases when you're coding it. Like, that's the beauty about Quicksort. You code it and it either sorts the thing or it doesn't. And there's no easy way to debug it other than like looking at it line by line. Because like with merge sort, you run it and if like most of the list is sorted, but like all the odd numbers are out of order, then this kind of gives you a point of what's messed up. With Quicksort, it's just like it either spurs out a sorted list or it recurses forever, or it just gives you some random data. So yes, have fun with that. Let me know if you need help and let the TAs know. But so somebody asked about extending the assignment. I can extend the assignment after the test. I'm okay with that. But I'm warning you. I highly encourage you to do the assignment before the test, because that's okay. Right now, hopefully you have a grasp of Quicksort. But when you're really gonna understand Quicksort is when you're actually coding it and you hit all these weird edge cases, and then it's gonna make sense at that point. That's why coding is great in that sense. If you code it, then you understand it. So I highly encourage you to do the assignment before the test as a way of studying for these algorithms. It's really, really it really, really will help. So yes, I will extend it to the weekend, like to the weekend after the test. So just next weekend, basically. But don't just procrastinate it. Do it ahead of the test, because otherwise you're not really gonna understand Quicksort. You will understand the algorithm after you code it. That's when you really understand it. So yes, I will extend it, but like I'm doing everything possible to really, really beg you that you should really do it before, because you will understand Quicksort much better. It's like how to make money. Step 1, do this. Step 2, come up with an amazing idea. Step 3, profit. The second step there sounds easy in English, but when you're coding it, it's a lot harder. You know, so like that's the thing about coding. You really analyze the atomic steps that you have to do to achieve something. So that's my preach for the day. But yes, I will update the deadline at some point. I just have to actually go on campus and do it. So yes. All right then, we're over by 10 minutes already, so I don't want to keep you guys. I'm also starving too, so I shall go eat, and you guys shall go enjoy the rest of your evening and your weekend. That's the South Park episode? Is it? I don't really watch South Park, but I believe you. I mean, the whole like step 1, step 2 profit, that's just an old meme, but it checks out. Yes, no problem. And since I didn't say hello there, I shall say, may the force be with you all. See you all later.